J'arrive. Allô?
Hi.
Good morning.
Good morning. How are you?
All right. How's everything?
Good.
How's your Corona life?
Actually, it doesn't affect my life that much.
No?
No.
And how's your family in Iran? Is your family okay?
Yeah, they're safe. They're good.
Yeah? Okay. Okay, good.
Yeah, but they still don't leave home. But, you know, they have started work
Okay.
in the offices and somewhere, but my parents are still at home.
Okay. Okay. So there was a lockdown also in Iran?
Yeah,
Okay.
but
Okay.
not that much serious.
Oh, really? Okay. Huh. Well, such is life. Hello, Shadi. Good morning.
You too, thank you. How are you?
I'm all right. I'm all right.
Perfect.
I was a little late in getting ready this morning. The kids were all excited, and everyone woke up fairly late. So, oh well. So I think everyone else also is. Valérie seems to have problems connecting, and we have a few others missing. But oh well. So let me do a few things. I think I have both of your assignments. How were the assignments? How was the assignment?
I sent you a Slack.
Yeah, yeah. I'm reading it now. Okay. Yeah, okay. All right.
Allô?
Oh, allô?
Hi.
Qui est là? Qui est là? Allô?
Est-ce que vous entendez en écho?
Non. On t'entend en tout court.
Perfetto.
Perfecto, perfecto, perfecto. Il y a eu un petit peu d'écho. Non, c'est pas vrai. Il nous manque Émile. On a...
Qui a fait l'écho.
Hein? Ouais.
C'est toi qui as fait l'écho.
T'as tout deviné.
Oh! Je suis choqué.
Oui. Mon imitation d'un écho est particulièrement...
Ici, il n'est pas là, je peux le texter.
Oui.
Moi, il parlait sur Messenger. Moi, il dire « Hey, Emilio! »
Hey, je suis là.
Oui, Émile est là. C'est Julien qu'on n'a pas.
Ah! Je te voyais pas, Émile. Allô?
Il vient juste d'arriver pendant que tu parlais.
Ah, ben torieux.
Tu m'as invoqué.
Parfait.
So obviously, you know, when people show up late online, everyone knows.
Yep.
It's
Especially
hard.
when we're so new in a.
It's hard to hide.
Yeah.
So are we waiting for Julien? So the assignment, was the assignment difficult? It should have been easy. Was it easy or was it difficult?
Mhm.
Valérie?
It wasn't.
Was great.
Uh-huh. Okay. Vincent?
It was fine. There was some little tricks that I didn't like, that I didn't get really quick, but
Okay.
after, I mean, it was great to remember how to do
integrate.
linear algebra and
Okay.
matrices, and once everything lined up, it was
Okay. Okay.
pretty easy indeed.
Okay. Okay. I didn't have time to look at all the assignments. I received most of them last night. Well, yesterday, but I'm guessing it's going to be fine. I'll grade them as soon as we're done with this. So, Valérie, did you text Julien?
Yeah.
Yeah. Okay. All right. We'll go slowly. We did the ABCD or array matrix formalism, but there's something else that in a more advanced course I would go through, but I don't want to take all of the course just for the formalism. So I will actually leave it as reading for you, but I will tell you the key things that are important. And it's we have looked at how we can trace the rays in infinite elements, an infinite lens. Everything is infinite, and the second thing that makes the formalism very appropriate is the use of finite lenses. And once we have finite lenses, you obviously understand that as we trace the rays, they will get blocked. So that part is, it's easy to understand that it will have an effect, obviously. But there's a concept, there are two concepts that are important when we start using finite lenses. Finite lenses we call apertures. An aperture is a, you know, an obstacle with a hole in it. So the hole is the aperture. So once we start using these apertures, there are two important apertures in a system. One of them is called the aperture stop. The other one is called the field stop. And I don't want to go through that because today I want to talk about detection. And if I did talk about it, I would need to talk about it for a long time. But I have documentation about this. And it is important for you to know what these are. So the aperture stop, I will give you my, Allô, Julien? I will give you my notes on the aperture stop and the field stop. And it's using this that we can fully characterize a system. The aperture stop is what limits the cone of light, and the field stop is what limits the field of view. Okay, so I'll give you my notes. It's not particularly difficult, and actually I think I already gave you my notes about the field stop and the aperture stop when we started the course, but it doesn't matter. It's not very difficult, and I will come back. I will, what I'll do is that I'll give you one small problem related to this reading, which you will do on your own, okay? So, because you have so much time on your hands. Okay. Yeah, so aperture stop and field stop are the final concepts we need to fully characterize a system. Okay. And in the ray tracing program that I that I gave you or that I told you to download, which you should have downloaded, this is considered. So if you understand what the concept is and you use a program and it mentions this is the aperture stop, this is the field stop, then you should have enough for at least using it. And yeah, the final the reason why I want to mention it is that the field stop is often a problem in the systems that students and professors build. It's the one that's off. You know, when you if you have already tried to build a microscope or an illumination system and the light, let's say you have your camera and you only have an image in the middle and you have black on the side, you know, it's all dark on the side, that's because your field stop is incorrect. Okay, it's not in the right place. Okay, so I'll give you my notes and I'll give you a small problem related to that. Now, the second thing that I want to do, where is my problem? Yes, right here. Okay, I want to show you this. It's coming. Where is it? Where is it? Yeah. Okay. So everyone sees this?
Yep.
Okay. So last year when I gave the course, we worked on this for a long time. Okay, this was the problem that I gave the students. And what is the problem? This is a microscope. That's actually a microscope from my lab. And we went through all the calculation to try to figure out what is the resolution of the system at the sample and what is the field of view. Okay, so this is the type of calculation that you would want to be able to do once you've fully understood the ray tracing formalism and the aperture stop and field stop. Okay, so we will not do that this year because last year I had the last year in the course I had 5 physicists and engineers who had taken my optics class as undergrads. So they knew already about the field stop, the aperture stops, and you know, all that stuff. But the point is, from the ray tracing formalism, you have everything you need to perform this calculation and tell me, for instance, okay, let me explain why this is a question. Okay, so if let me, okay, give me a second. I'll take my iPad instead of my computer, so I can write on the screen. Where's this? Okay. It's coming, just a sec. Okay. All right, perfect. This, where's my iPad? No, not this. Yes. All right. Okay. So everyone sees, yeah, everyone sees the iPad? Okay. So why is this even a question? What is the question? Okay. What is the question? In some systems, we scan a laser and although we always just assume, yeah, the light will be scanned and then I'll get an image, we understand the concept, but at some point the details are important. How far am I going to scan? So what I would like you to appreciate and understand is that if we scan, let's say, a certain angle here, and there's a certain lens and another lens, and we scan another angle here, and there are lenses, you understand that if I scan a beam, it's going to go from one point to another. If there are limitations and apertures, or if I'm limited in my angle, then the beam will reach different points. So the calculation to see where the beam goes is just an application of the ABCD matrices from here to here to here to here to here. So in the end, we can get where the beam is scanning at the sample. And I would love to have you do that calculation as a small simplified assignment that I will give you tonight. Okay, so that's the plan. And the reason why I really like this is that I really try to have this imaging course be practical. Okay, so there are aspects of design. There are two things, and I'm kind of looking at all of you here differently. Let's say Shadi, Elahe, and Emile may design microscopes as physicists and engineers. So you would know, where would I put this? Where would I put that? Whereas Vincent, Valérie, and Julien, I would like you to understand why it was put there and confirm that it's in the appropriate position. So there's a difference between recognizing that it's done okay and figuring out how to do it okay. So with the formalism that I'm giving you, the engineers should be able to figure out all the details, whereas the others should be able to confirm that from this design, this is the type of field that I get, this is the resolution that I get. Okay, whereas the engineers would say, oh, I want to improve the resolution, I want to get this different resolution, this is what I would do. Okay. All right. So I'll ask you a question regarding this tonight. Okay. Give me a second. My kids are yelling. Just a sec. And I am back. Okay. Okay, here I am. Okay, so moving on to today. Okay. Today we're talking about a detection. So we have everything we need. Okay. Yeah. All right. Okay. So we have everything we need at this point to. We should have everything we need to. Non. Tu pouvais être ici, Rémi. We have everything we need to build the system and send the light where we want to send the light. But now our plan is to have a detector that will detect the light and help us rebuild the image. So what we're going to do today is, and again, I apologize to Elahi and Shadi, the slides are still in English. I will need to translate everything at some point, but I'm guessing, how bad is it that it's in French? Did I say English? I meant French. So how bad is it that this is in French? Can you kind of understand or figure it?
Yeah, because just you are talking in English, you are speaking in English, it's okay.
So then
you're explaining the details.
Okay, so then you can kind of make out the words. Okay.
Yeah.
Okay. All right. So today our plan is to figure out what is the right detector for the job. That's really what we're going to try to do. And this is important because at some point we have to figure out, is detecting this amount of light possible, and what is the best detector to do it? Sometimes you know that there are cameras that are $50,000 and there are cameras that are $1,000. So what is the difference between, you know, why is one 50 times more expensive than the other? So we we would like to know, because if we can purchase the $1,000 camera, why would we buy the $50,000 cameras when we can use the $1,000 camera? And same thing, if we have a small detector that that costs 10 cents, if it's sufficient, why would we buy a $5,000 detector? So that's what we're going to do today. And to do this, we need to have an idea of the parameters that are interesting for when we look at light. So if I talk about irradiance, does that mean anything to anyone here? If I say irradiance, what is irradiance? 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 Anybody has an idea? The units of irradiance?
It's the power for a certain surface, a certain area in time.
Not bad. Excellent. So irradiance is the amount of power we have per surface. Very often it's called intensity, or people will refer to that as power sometimes. So it's a word that is used and misused. So the thing that we're most of the time interested in is not just power, because if I have a lot of power over a large area, then I will not have a lot of photons in a small area hitting my molecules. So the power itself, the energy is just the number of photons, and the power is the photons that I get per second. If I get a lot of power, a lot of energy, but over an extremely long time, I have very few photons per second. If I have a very good power, but over a large area, I don't necessarily have a lot of power per area, obviously. So the thing that will interest us the most is the irradiance. And it's interesting to have an idea of what these numbers are. And what I would like you to know is what is the irradiance of the sun? Anyone knows what the irradiance of the sun is?
I don't remember.
Me neither.
No?
No.
Okay. I really like to discuss this because it's a number that's easy to remember. It's 1,000 watts per square meter, approximately. Okay, so we all know that 1,000 watts. Well, when we look at the sun, we don't look at the sun. We don't stare at the sun because it hurts. Okay, just a second. So we don't stare at the sun. So we know that 1,000 watts per square meter is a lot of power per surface in our eyes. And what's the typical power of a tiny little laser? So, oh, I'm sorry. 1,000 watts per square meter is 100 microwatts per square centimeter. Okay. I'm sorry, 100 milliwatts per square centimeter. Sorry. 100 milliwatts per square centimeter. So what is this for a laser? Well, a laser will have a milliwatt in a very tiny area. So we can get very high, very high powers per area. And the second thing that is important is that we have, the sun has a lot of colors. So it's all this power that is in the 1,000 watts. When we are interested in exciting a molecule, let's say a green fluorescent protein or some molecule that has just a small absorption spectrum, then we want all the power to be in that wavelength range. So the spectral irradiance is the amount of power that we can get per surface per band. So how is this different? For the sun, okay, the sun has 1,000 watts and per square meter, which is 100 milliwatts per square centimeter, but it's a large or a very broad spectrum. So we end up with, as I was mistakenly saying before, 100 microwatts per square centimeter per nanometer. Je suis en train de, ça sera pas long, je suis en train d'enseigner les garçons. Il faut que vous attendiez. OK? So 100 microwatts per square centimeter. But for a tiny little cheapo laser, like a helium neon laser, then typically we'll have milliwatts, a few square millimeters, and we'll get 1,000 watts per square millimeter per band because the color is very well defined. And that's just a tiny little laser. So what I'm trying to tell you is that when we look at the sun, we don't stare at the sun because it's too bright. And a tiny little laser like this, a helium neon laser that we are using for alignment purposes. You know, this is just a, you know, those red laser pointer. It's essentially a laser pointer that we use, you know, that we can buy at the convenience store. You know, this is millions of times more intense. Okay, so the detectors that we have will need to be able to see very intense beams, but at the same time, sometimes when we do fluorescence, we may get just a few photons, because we discussed that, unless I'm mistaken. I think we discussed picowatts and nanowatts and you know, a few photons per second and things like that. So sometimes we have very small amounts of light, and sometimes we have very large amount of lights. So what we're going to try to do is to figure out what is the best system to detect this light from a few photons every now and then to very intense powers, much more intense than sunlight. Okay, so we need to have a tiny little bit of electronics, just a little bit, okay, just a little bit. So Elahe, that's going to be more very, I think very natural to you, but it may be also for Shadi. It may be less natural to others, but we need to, again, we're looking at this problem two ways: designing a detector, or at least pick the right detector. So my goal here is to make sure you can pick the right detector. Okay, so what our goal is that we need to talk about electronics a tiny little bit, because the way we detect photons is by having a photon hitting a certain material, and the photon will create an electron, and then we'll measure that electron with electronics. So if we detect a small current, we'll just say every time that I have a certain number of photons that are creating a certain number of electrons, then if I measure 1 electron per second, I had approximately 1 photon per second, for instance. So the goal we do electronics because there's a mapping almost one-to-one between the flux of photons and the flux of electrons. Okay, so when we have a detector, we all have at least one detector that we know. And what is that detector? Our eye. Okay, we all have at least two eyes. Okay, most of us. And the eye is actually a very sensitive detector. It can detect a very small number of photons. Apparently, we can detect hundreds of photons. So we don't need tons of light to be very sensitive and see something. And the difference between the eye and everything else, all other materials, is that the eye has a certain sensitivity, and we only see in what's called, obviously, the visible light. So the eye has a spectrum that goes approximately from 450 to approximately 650, very much approximately. And beyond that range, we don't see anything, okay? So if there is a lot of power at 700 nanometers or 800 nanometers, we will simply not see it. That doesn't mean it's not there. It simply means we don't see it. So lasers that operate in the infrared are dangerous because they will still burn your eye and your retina, but you will not see that. Okay, so the eye has just a certain range that is usable, let's say, and you will sometimes see a special unit, and that unit is called the lumen. Okay, a lumen is something that the eye sees. So, for instance, if you receive let's say 1 milliwatt of power in the green, you will see it very well because we're very sensitive in the green. If you receive, so it's a lot of lumens. If you receive 1 milliwatt in the blue or nearly UV at 400 nanometers, then the eye will not see it. So therefore, it's a nearly zero lumens, because the lumen is the power as perceived by the eye. So it's really the power multiplied by the sensitivity curve of the eye. Okay. Okay. So now what we're going to try to do, okay, is that we're going to try to figure out what are the various systems that we can use with detectors to and see the range of powers that they can see. So for this, we'll need to know a little bit about the optoelectronic properties of the materials and the electronic properties of the circuit. So now you're thinking, I'm thinking of Valérie, Vincent, and Julien. You're thinking, oh, good Lord, you know, materials with optoelectronic material properties and electronics, you know, two things that I don't know much about. Well, again, please keep in mind, I'm not trying to make you build and construct new detectors, but identify which one's the right one. Okay. So I do have an analogy for electronics, because if I were to talk about electronic, if I say voltage and current, you know, Vincent, Valérie, and Julien, what do you guys think if I say voltage, currents, resistance? What do you say? You say, oh, good Lord? Or do you know a little bit? Do you know a little bit about what do you know about electronics? Tell me about electronics. Voltage. If I say voltage, huh?
You don't know.
You don't know, Valérie?
Resistance is what enables you to toast your toast. And
Very good. Yeah. So
And
Resistance.
current is like the number of electrons per
second.
time. Second.
Yeah. Yeah.
Going through a point.
But
And
voltage.
voltage. Yeah. What is voltage?
Voltage is what drives a current. It's what
so it's like the speed.
Electrons move.
It's what makes it move. So think of this, okay? I really like the water analogy because it's close enough. Okay, it's not perfect, but it's really close enough. So if you think voltage, okay, voltage, by the way, in French, it's tension. Voltage, voltage is not the right word, but although everyone uses it. But anyway, so the voltage is like pressure in a pipe. So you can have a certain amount of electrons per second, but pressure is what's going to push the water. So the voltage and pressure are very much related. And how do you get pressure in a system? With a pump. Well, the pump is the battery. So the battery, when you connect the battery to your system, then you will push the electrons. So you provide pressure, you provide voltage. And then these electrons are going to start flowing, and the flow is the number of electrons per second. Well, it's the same as the amount of water per second, or the flow of water. And then the resistance is interesting, because if you have a lot of resistance, then it's hard for the water to go through. Well, a low resistance is a big pipe, and a high resistance is a small pipe. Okay, so if you think of this analogy, usually you have enough to understand or get an intuitive idea of what's going on in an electronic circuit. Well, obviously, the best is to eventually understand what a volt is, and current is, and a resistance is. But I know that from experience, I know that even for physicists, you know, it takes sometimes. Okay, the intuition takes a certain time to develop. So, with the analogy, pump, pressure, water flow, and size of the pipe, you can at least get an idea of what's going on in the system. Okay, you may want. So I'm assuming that for Elahe, who's you're an electric engineer, right?
Yeah.
So I'm assuming that this is a little simplistic, but Shadi and Emil, I don't think that you're necessarily very at ease with electronics. I assume that you know very little. That's fine. And Vincent and Valérie and Julien, I'm assuming that for you, you know that it's very little. So there are two things. First of all, there are references. Okay, I really love these references. Okay, this here, the art of electronics is considered the Bible in electronics for everyone. It's an intense book. Okay, but it's the Bible. So someone who really wants to know, learn from the start, this would be the book to say, okay, I want to be the best in electronics. I have this book in my office, by the way. But it's, as I said, it's very intense. It's not an easy book. There is another one that's also particularly excellent, called Building Electro-Optical Systems. this is actually, this I would say is probably the book for Shadi, Emil, and Elahe, because it's electronics for detection. I also have that book. And so this has, it's actually a very funny book, by the way, because it's written like a discussion almost. So Phil Hobbs is really he's a good storyteller. So the book is actually fun to read. Fun, as long as you want to read about electronics. But there's tons of information in this book about, oh, come on, you don't use this detector like this, you know, use it like this, or we see this circuit all the time, but that's not the right circuit, or blah, blah, blah. So this is, I find, is somewhat accessible. So if you know a little bit of electronics, but you're really trying to figure out, oh, you know, what's this noise problem that I have, or, you know, this is where you would go. Okay, so again, as I said, I have this book and you can borrow it. I even have, I think, a PDF version. And the final book that is very accessible is this book, the Handbook of Biological Confocal Microscopy. I also have a PDF version of this. And this has 30 or 35 chapters. And some of them are about detection. So this is very accessible. So for instance, there's a chapter entirely devoted to photon counting. Why would you do photon counting instead of analog detection? That's something that we have, you know, later in the discussion today. But this will actually explain and then show examples for why this is a good strategy sometimes, not always, and will show very, very basic circuit on how to do that. So this I really like. And I think it's accessible to any graduate student. So, and there are tons of also very good chapters on fluorescence, and everything is in that book. This is also a great book. I also have this paper copy of this, and probably a PDF copy. Okay, but I do have a paper copy. Okay, so these would be the references that I would recommend to everyone. This is by far the place to start. Okay, this is clearly the place to start. Oops. Okay, whoa, what happened here? Yeah, okay. So I got a. Yes, when in doubt, yar. Okay, yes. Okay, I get the message. Okay, so all right, the reference. Okay, then so coming back to our the problem at hand here. So we have this batteries, voltages, currents, and resistance. One thing that people have to appreciate. And to be honest, it took me a long time to appreciate or see why this was the case. We know that when we do when you do an electronic circuit, you can measure voltage, you can measure currents, but then we're always, we always talk in terms of batteries, and batteries provide voltage. And I know that I was always surprised. And I thought, why don't we work with current? You know, why don't we have a battery that provides 1 milliamp? Or why don't I never understood? Well, I never understood. That's not true. Now I do understand. But I always wondered, why do we work with volts? Why couldn't we work with currents? And say I have a 1 milliamp battery and I have a resistance. So when I go through this resistance, the voltage the voltage drops by this much, et cetera, et cetera. So the reason why we work with voltage, you may remember from college. Okay, you may remember from college. Measuring, Vincent, Valérie, Julien, anyone, you know, what do we, how do you measure a voltage in a circuit? You must have done that in Cégep. You must have done, you know, a battery with a resistance, and then you measured the voltage and you measured the current. How do you measure the voltage and how do you measure the current? Do you remember? Anyone, actually. I'll take an answer from anyone except Elahe for now. Anyone? So how do I measure voltage? So let's say I have a multimeter or an oscilloscope and I want to measure the voltage somewhere. How do I put my multimeter in the circuit? You know, how do I measure?
Okay. Yeah, the voltage is measured in parallel.
In
and the current is
parallel.
measured in
Series.
series. Yeah.
Yes. Okay. So if I have a circuit, I don't have a figure for this, but I don't have a schematic. But when you have a circuit and you're trying to measure the voltage, you come with a multimeter and you just insert, you take your two probes and put them in parallel in your system so you don't disturb the system and you don't break the system. If you want to measure the current, so let's say if you want to measure the water flow in a pipe, you need to put something, you know, inside the pipe. Okay, so if you measure pressure, you can just put something at the, you know, on top and measure without really going inside, because the pressure is all around, but the flow is inside. So voltage, you measure in parallel, but a current, you need to take your multimeter and put it inside the circuit. So that's outrageously inconvenient. So if you had an electronic circuit and you said, oh, I really want to know what's going on in this wire, you would cut the wire, take your multimeter, put it in, measure, and say, now my circuit is broken. What do I do? So voltage is measured in parallel, which makes it by far the best thing to work with because you can measure at any point without breaking your circuit. So we always work with voltages because it's the easiest thing to measure. Okay. All right. So just note that measuring volts is very easy. Measuring millivolts and small millivolts is possible. You know, a few millivolts is possible. It's very difficult to measure microvolts. Okay, because in a circuit, it's fairly in our circuits. Let's call that our circuits, you and me. You know, the electronic noise in voltage is usually a millivolt. You know, the noise due to a circuit is millivolts. Why am I telling you this? We're going to go through a few detectors in the next few slides. It's coming. And when you go to the Thorlabs website or Newport or any other company, at some point they'll say number of watts, number of volts per watt. Okay, so they're going to give you the responsivity curve of your detector. And they're going to say, if you send a milliwatt, you will get, let's say, a millivolt or 10 millivolts or 100 millivolts. So what you have to remember is that if that number is less than a millivolt, then it's going to be hard to measure. If it's above a millivolt, it's possible to measure it. So the millivolt range is really the threshold. You know, if you have a signal that's less than a millivolt from your detector, you know, you're going to have to work a little. If it's a signal that you can get that's in the hundreds of millivolts, then that's fine. We can work with hundreds of millivolts. And that's how, when I sit down with my students, when we pick a detector, then that's the thing that I'm going to do. And I'll say, how big is the signal? And if we get microvolts, I say, no, that this is not going to work. And if we get hundreds of millivolts, I say, yeah, this we can do with a very simple acquisition system. So millivolts is the threshold. Give me a second. I'll just close the door. And I'm back. Okay. So, all right, let's dive right into it. Can you name me various types of detectors? Anything. Name me detectors.
A
What are they?
CCD.
A CCD? Yeah.
Yeah, a photomultiplier tube.
A photomultiplier tube.
A CMOS.
CMOS? What's a CMOS?
It's used in almost a phone. Yeah.
A what? A
CMOS. It is used in the phone for a phone camera.
So it's probably cheap to make. Anything else? I'll need more than that.
Photodiodes.
A photodiode. How do you measure power? Valérie?
PMTs.
Yeah, a PMT. Shadi said photomultiplier tube. Yes, that's the PMT. Yeah. I'll deduct points for that. That's you can't repeat what someone has said. Okay. Anything else? So photodiodes. Are there many types of photodiodes, or many types of ways to use photodiodes?
Yes.
Yes.
Definitely.
Yeah.
Photodiode array.
Photodiode array. Yeah. That is true. I don't have that in my list, but yes. And how about let's say you have a big, powerful laser and you want to measure the power. What
power meter?
Yeah, a power meter, which will detect, watts. Okay, so we're going to go through this list today. That's what we're doing. All of this. Okay, so there are thermal detectors for power. So this is when we want to measure watts, and I have a summary table at the end. But we're going to go from watts to just a few few photons per second. So super high power, super low power. And then there are cameras, and there are CMOS cameras, SCMOS cameras, CMOS cameras in your phone, a few cents per cameras. SCMOS, $50,000 for a sensor. So they look the same. S is for super expensive. That's not good. It's for scientific CMOS. And then CCD and EMCCD. We'll go through all of that. Okay, so those are image sensors, and these are point detectors. So they detect they give a current or a voltage per electron. So let's start with the easy one. Okay, we recognize these. Okay, the sensors like this. Okay, if you look at the sensor in the hole here, everyone has seen a detector like this, I'm assuming. Julien, yeah? Yeah, okay. Okay, so this looks like plastic here. Okay, it looks like almost like tissue or cardboard. Okay, it's not glossy. Okay, so this will simply absorb all the power, transfer it into heat, and inside there's a heat detector, and depending on the heat it will give a certain value, and this will give you the power. Okay, so this is really a detector for detecting large powers, like laser powers. So you have to be somewhat careful in the lab, because these are called heads. So when you use, let's say, this is the controller and this is the head. So you can usually change the head of a controller and just plug in different sensors. Okay, so sometimes a sensor can accept tens of watts. 10 watts is extremely powerful, by the way. It really hurts, okay? Above a watt, actually above 200 milliwatts, it hurts. If you put your hand in more than 200 milliwatts, you feel the burn, okay? So 10 watts, it hurts a lot. So if it hurts you a lot, it can hurt the photo detector also. So these heads have, usually if you look at the back, it's going to say this detector is for no more than 5 watts, no more than a watt, or no more than 100 watts, et cetera, et cetera. So it's important because there are detectors that will not take more than a watt. And we have a lot of lasers that are 3 and 10 and 50 watts and 60 watts. So you have to be careful. And just because it works with the controller here, so very often the most common now have this thing here. The connector that you connect into the controller will have information about the head. So when you connect this the controller to this detector, this here will provide the information to the controller and will say, yes, here I am and I can measure this and I can measure from here to here. So at least the controller will know what to do. But you have to know that you shouldn't send too much power into a certain detector. Just because it works with the detector, the controller, doesn't mean that you can send anything you want. And I purposely tried to use these two because they are different. So some of them here, I insisted that these look like cardboard little, non-glossy thingy. Okay, it really looks like burned cardboard or plastic or nylon. But there are others that are not like that. And they also work with these controllers. And they look glossy. Sometimes they have an attenuator, a glass attenuator in front. And if you remove the attenuator, what you see inside is, it looks like a mirror. It looks very shiny. The shiny ones cannot take a lot of power at all, okay? So they are very sensitive, okay? And they will burn if you send more than 100 milliwatts. So it's very important to know exactly what you have. You will notice if you go in my lab that many of those, if you look at the attenuator, many of them have burnt spots because they were used with too much power. And sometimes you may not see that on the attenuator, but if you unscrew the attenuator, then you look inside and you'll see the shiny detector, you'll see burned spots or even cracked spots. So you just have to be careful that you use them properly, because what they want to provide, the companies, so this is a Newport detector, but we use a lot Gentek EO, because it's a company from Quebec City. All they want to give you is an opportunity to measure your power from very low to very high. So they have different heads, but you still have to pick the right one when you use it. Okay, so that was my little 5 minutes of lab teaching to not bust equipment. Okay, and each head is $1,000. So we just have to be careful. And I should have, I guess I could find it on the web if I wanted to, but there's a super tiny detector we have at the center that looks, I'll find it on the web. If I can be quick, I could, that would be, it's called the Magic Wand Power Detector. Let me see, do I have it? No, Newport. If I type Newport, I should get it. Yes. Okay. So I'll show you my screen. Whoa, where'd you go? Okay. Yeah. Okay, so I'll show you my screen here. Chip. Where's my screen? Okay. Okay, you can see my screen?
Yes.
Okay, so this detector, do you see this detector? It looks like a wand. So this detector here is so that you can insert it under your microscope objective. Okay, so it's very sensitive because it can measure very low powers. The one we have, has quite a few holes because some people have used it to measure the power of the laser before. And I will say, that's fine. It happens, okay? And if you have done it, that's, yeah, it's unfortunate. Just don't do it again, okay? So, yeah, so there you go. That's what I wanted to show. Going back to going back to this. And here we are. Okay, so power detectors. Okay. Yes. Okay. Now the meat. Okay, the meat. A photodiode. How do photodiodes work? Okay. A photodiode is the most, with the PMT, it's the most common detector that we will use in a lab. Okay, so we don't need to know the details, okay? But a photodiode is a semiconductor. So it's not a conductor, it's not a resistor or a metal, it's something in between. The name of the detector will often have the name of the semiconductor. So we will say, oh, this is a silicon detector, or this is an in-gas detector, or this is a gas detector. So you don't need to know all the details about these semiconductors and the fact that there's a certain region called the P region and the N region. You don't need to know that. What you need to know is that the name of the detector is the name of the material that absorbs the light. So if you have a silicon detector, it will give you light in a certain range, and an in-gas detector in another range, okay? And the way that we use these detectors is fairly simple. Every time that one photon enters the material, the detector, so the light will enter here through the detector. In the semiconductor region, one photon will create one electron and one hole. It will create both. And then it will create one negative charge and one positive charge. So it's all you have to remember, really. So then you'll have a current that will flow, or that should flow through the connectors of this detector. So you shine light, one photon, you get two electrons that, if you have enough pressure in your pipes, will just start flowing. If you don't have water, if you don't have pressure in your pipe, if you don't have a voltage, they'll just stand there and eventually just, recombine. So we take a photodiode and then we'll connect it to a battery, to an amplifier, to something, so we can get these electrons. Because if we don't do anything, they're not going to go anywhere. Okay, so we'll see that that's what I'm doing in the I have 7 slides on the various ways we can connect this, and you'll have to bear with me, but you need to appreciate the various circuits associated with that. And as I said, the material will give you the range where you can use the detector. So a silicon detector is very, very common. It is by far the most common because it's cheap, because it's everywhere. Okay, so and all circuits, CPUs, chips, etc. They're often made in silicon. So silicon, and silicon comes from sand, and there's a lot of sand on planet Earth. So silicon, you know, that's awesome. We can do silicon. Okay, and what you must notice is that, remember that silicon will detect everything in the visible up to 1 micron, 1,000 nanometers. So that is actually important because, for instance, in Shadi's project, we have a laser that operates just around that range. And we're in a, you know, when we can, you know, we're trying to work. It's very convenient to work in the range of silicon because silicon detectors are cheap, they're common. There's a lot of things we know about silicon detectors. And if not, there are other detectors like the gallium arsenide detector that will be more sensitive, but and faster for tons of other reasons. But it's essentially like a silicon detector. The other one that you'll see very often is the indium gallium arsenide detector, which you can see with the silicon detector and the in-gas detector. Then you cover a very, very broad range. So in the infrared, the in-gas detector is fairly common because germanium detectors are a bit fragile. So in-gas, good for infrared, and silicon, good for visible up to infrared. Okay. So this is what a silicon photodiode looks like. Okay. So very often, I'm assuming most of you have seen something like this. Yes? No? Maybe? No? No? Okay. Okay. So this is very small, right? This is a few millimeters. This is like 5 millimeters, and this is probably 7 millimeters, something like that. And the detector is really the square part in the middle. So that's what it looks like. And the circuit that the schematic we use in a circuit is something like this. So it's an arrow that points in a certain direction. So it says, what this says, it's a photodiode because the current will always flow in the same direction. So in a diode, the current flows in the direction of the arrow and doesn't flow in the opposite direction. So when you have a photodiode like this and you shine light, then it will generate a current that will go in this direction. Okay. All right. Yeah, that's what I had here. So if you apply pressure, if you put a battery from here with a positive voltage and a negative voltage here, so the voltage goes from high to low in the direction of the arrow, that's good. You have a current. The term for this is called forward biased, okay, as in you're pushing in the forward direction. If you do the opposite, then if you put a positive voltage and a negative voltage in the opposite direction of the arrow, then you just don't get a current. At some point, if the voltage difference is way too high, you will get a current, you'll just break it. But usually, say for the sake of the discussion, positive to negative in the direction of the arrow, you get something. The other direction, you don't. Okay, so there are now 5 modes to use these photodiodes. It's essentially always the same photodiode, but the way you use it will provide different results and different signals. So the very simplest thing to do with a photodiode is to just use the photodiode like this photodiode like this, and put a voltmeter at the tip here and here. How about that for a simple circuit? Well, that's extremely suboptimal, but if there is light, you'll see something on your voltmeter. Okay, you'll see something because light will hit this, it will generate, poof, a few electrons. And if you have electrons here, electrons here, and positive charges on the other side, and you're measuring the voltage, you'll see something, and you'll see a current. You'll see something. That's fine. But if you're not providing pressure, if you're not providing a battery, then they're just gonna stand there and eventually disappear. But you'll see something. Okay. So just to be clear, that a detector will provide a signal. It's not a good signal, but it's a signal. Okay. And whenever when you shine light, okay, it will. Oh, I hope I don't have this the wrong direction. If someone can help me, I'm quite sure that the charges go. Do I have this right? Can someone confirm that I have this right or wrong? But it's because it's the charges go either plus or minus and plus.
I think it's right because I think the convention is plus to minus.
Yeah, but I'm not
Even if
sure.
It's not the same sense of the electrons. It's the opposite.
Yeah. But I don't know if it's in this direction for the photo. It doesn't matter. Okay, let's. I don't remember, but I'm quite sure this is correct.
If you're talking about the positive and negative voltage in the current, it's correct. But for the for diode, I think it's the reverse.
So you think I have it opposite?
For just a diode, yeah, it's opposite.
Okay.
Because it will have a voltage about around 0.7, and it's in the opposite direction.
Okay. Well, I'll double. Okay, I will fix this. I promise. So, let's just say that for now, I don't remember if it's plus or minus, but if you connect it, you'll see something. How about that? So the sign of what you'll see, I'm not sure anymore, but now I really want to know.
Is it that because when you don't have light, you don't want to there to be a current, so it should be
So if there's no light, you will see nothing. It's going to be 0, 0. So, and as soon as there's light, the charges will separate, but I don't remember which way they go. Is it like this or like that? Is it plus minus or minus plus? I don't remember. So that's what I'm trying to figure out, but I don't remember. And Elahe seems to say that I have it opposite, so I'll double check. Okay, but anyway, that's the simplest. That's a very dumb circuit. Okay, nobody would ever do that really for a real circuit. There's let's say if you want to connect it to see, let's call that a relatively slow signal, and you don't want noise, we use the mode called photovoltaic. You don't need to appreciate all the details. This is called an amplifier. We don't need to understand that, okay? So those who need to understand this, Emile, Elahe, and Shadi, don't really need to know all of the details, okay? But this is called a transimpedance amplifier. The point that we need to remember is that this mode, when we use it in this mode, it will tend to be limited in speed, but for most of what we do at the servo, speed is not an issue. usually, not always, but usually. So this is going to be relatively slow, but not noisy. Okay, so every time that you generate an electron or a current here, the current will go through this resistor, will increase the voltage because there's an amplifier. So here you'll get a voltage. So what this does, okay, this whole thing, well, what is this whole thing doing? It's taking a current from here and changing it into a voltage here. Okay, because I told you we want to have a voltage because we want to measure in parallel and we want to connect things into our circuit without breaking the circuits. So we want this current to become a voltage source. Okay, what do we remember? What's the take-home message? Photovoltaic, not necessarily super fast, but optimal in terms of noise. Okay, there's every time you create, anytime a photon hits the material, it generates one electron hole pair. So let's call that one electron. Okay, it's two, but you'll see. Okay, there's no amplification. One photon, two charges. Okay. There's another mode called the photoconductive mode. And the photoconductive mode is very different. We use a battery that we put in reverse orientation with the diode. So we're really, it's like stretching a rubber band and, you know, pulling really, really hard. And as soon as an electron will be created, it's going to go zoom very, very quickly out of the diode. So this technique will be much faster. So if we're trying to see pulses, if we're trying to see light that goes very quickly, like megahertz, you know, microseconds or even nanoseconds, then usually we need something like this. So it's faster, but it's also noisier. Okay, so photoconductive, faster, but a bit noisy. Okay. Yeah, that's a detail for experts here, and I'm skipping it. Okay. Okay. Then the third mode is called an avalanche photodiode. So what is an avalanche photodiode? I told you that whenever we take light is incident onto a detector, we create one positive charge, one negative charge. Okay, so for one photon, I get, you know, a small current from two charges. I may push them really hard with a voltage, but I will always have just one electron in that direction and one positive charge in the other direction. There's no way to get around that. Well, actually, there's no way. With those photodiodes, it's one photon, two charges. The avalanche photodiode is different. What it's going to do is that you set up the diode in a way that you're pushing super hard on the diode. So the rubber band is stretched really, really, really tight. And when the photon hits the detector, it will create two charges that will be so energetic that they'll create another pair of charges, and they'll create also another pair of charges and another pair of charges. So for a single photon, you'll get 50 and 100 charges. That's really important. That's really relevant because the other two photodiodes that I described, don't have a gain. You have one photon, two electrons. The avalanche, you come with one photon, and you may have 100 electrons. There's a gain. So that means that if you work well, in the best case, in the regular photodiode, one photon will give you a flow of 2 charges per second if you have one photon per second. Well, in this, you could get 100 or 200 charges per second. Okay, so this gain here is really useful when you don't have that many photons per second, because I told you before, it's hard to measure a millivolt. Okay, I mentioned it's hard to measure below a millivolt. And now imagine it's hard to measure 1 electron per second, okay, a flow of 1 electron per second, because then you would need to go through a certain resistor, let's say 1 mega ohm, and then you'd get a very small voltage difference. Okay, so the point here that I'm trying to make is with a gain, you can go beyond the millivolt. You can get 50 millivolts, 100 millivolts from your small signal, and all of a sudden have something that is detectable. So avalanche photodiode are very fast. They're also very noisy, but they're very fast and they're very sensitive. They're obviously 200 times more sensitive than these other detectors that I described before. So you use an avalanche photodiode when you have a low photon count, which means a low power. Okay, and I'm keeping this, although it's not as relevant as it used to be, but there was something that came on the market but never really made it. It's called a solid state photomultiplier, but it's really hundreds and hundreds of avalanche photodiodes together on a single chip. I would have talked about it more 10 years ago and 5 years ago, but they have quite a few problems that at some point they were presented as replacements for photomultiplier tubes, but that did not happen. So maybe at some point, but imagine that you take this this avalanche photodiode, but you put 1,000 of them on a square. Then if you have one photon that hits one detector, you can have another photon hitting another one, and all of them can also all discharge at once, and you can get a big avalanche, and you can get a gain of 1,000,000. So one photon will give you 1,000,000 electrons, but for tons of technical reasons, there are things that don't. It's different. So that's for the experts in the room. So SSPM, solid state photomultiplier tubes, which brings us to real photomultiplier tubes that haven't gone away after all these years and are not about to go away. Okay, we'll finish. No. Okay, actually, yeah. Okay, why don't let's take a because I have quite a few things to say about the photomultiplier tube. Let's take a break here. Okay, let's take a break here. We can all go make a coffee, and then let's meet again in 5 minutes. Does that make sense?
All right.
Okay, 5 minutes. Hello. Sorry for the delays. Good Lord, the time flies. Okay. Okay, so let me know when everyone's here. We'll talk about the PMT. Is Vincent there? Vincent? 1, 2, 1, 2. Vincent?
1, 2, 3.
Oh, 1, 2, 3.
Je suis là, j'écoute.
Parfait. Bon, moi, je me suis fait mon café. Parle aux enfants. All right. Okay, so we're almost done here. We're almost done. We only have we don't have as much to go through for the rest. I hope that those who want to see the details see that I'm giving you enough for the details, and those who don't want all the details can at least get a practical sense of what I have to do, because that's what I'm trying to do in the course to satisfy to satisfy both Elahe and Julien, which I think to me are probably at the two extremes in this discussion, where Elahe is probably hearing things that she already knows, Shadi also, and Julien is probably thinking, what is all these voltages things? And Valérie too, and Vincent, I know. And I'm not I'm not pointing, I'm not, it's not a question, it's not a question of intelligence, it's a question of experience only.
And
just
interest.
And interest or disinterest. Yes. All right. So the PMT. How do we use PMTs? What are PMTs? Okay. A photo multiplier tube. Okay. It is the workhorse of fluorescence microscopy, and we'll see why. And actually, you should have an idea of why. I have a question for the group. So, from everything I've said so far, what do you think will be the key differentiating factor of a PMT compared to all of the other detectors that I described before? What do you think will be the key things? The key thing? What parameter, what property of the PMT is going to be very different from the photodiode, the avalanche photodiode? What do you think it's going to be?
It counts photons?
It can count photons. And Shadi?
It intensifies the signals more than others?
Yes and yes. So I love both answers. Valérie's answer is pragmatic. What can I do with it? And Shadi says, yes, it can count photon because it amplifies the number of electrons. So that's very good, very good. So yes, the gain of the PMT is extremely high. So how does this work? And again, let's try to let's look at the details because it has a pragmatic impact. So a PMT, this is just a schematic PMT, but the light enters from sometimes the side, sometimes the front, but it will hit some sort of a glass window here. Okay, and this window appears irrelevant to some extent, but that's where all the magic, that's where the detection occurs. So this here, this glass window is called photocathode. Where is it, or what is it? I'm sorry. The photon will create a photoelectric effect, or photoelectrons. So the material that's coating this glass window is really important, because that's what the material is will determine what type of photoelectric effect you will get. If you get a photoelectric effect with blue photons or red photons or fancy photons or purple photons or whatever. Okay, so again, like we had the silicon photodiodes, the in-gas photodiodes, we'll have a multi-alkali PMT, a gallium arsenide phosphide PMT, etc. So the name of the PMT is the name of the material on this, because it tells you what range of photons it can see. Okay, and I have a graph in 2 slides for this. Okay, but what happens is that the photons will hit this window and will create one photon, or one photon will typically create one photoelectron. And then that electron will be accelerated towards a big metallic plate, and it's going to accelerate so much that it will create more electrons that will explode out of this plate into this other plate, and then more and more and more and more and more. And every time that an electron hits another plate, it has accelerated so much that it creates more electrons, because it hits they're called dinodes, but the electron will come and then schlang, and one electron will create 20 more electrons. So it's a cascade that you start with one photon that creates one photoelectron, but then at the end, you have tons and tons of photoelectrons. Well, actually, tons of I know. They're not called photoelectrons at that point. The only photoelectron is the very first one here. At the end, you have tons of electrons. So you start with one photon, one electron, and then at the end you have 1,000,000 electrons. So that's very different, extremely different from the other detectors. The avalanche photodiode, I told you, could create 200 electrons, approximately. 200 electrons from one photon. Well, here we can create 1,000,000 electron for one photon. So we have a very large current for one single photon, because the gain is so large. So that's how, when we connect it in our circuit, we'll be able to see a single photon we'll see as a peak from the photomultiplier tube. Okay, and the things we need to remember is we select them from the photocathode material. So we have the most common, actually the one that I have in my lab a lot, is a multi-alkali PMT. And because it's very good, it works all the way up to, I have a slide for this in 2 slides, but it works to the range that is meaningful in confocal and the multiphoton fluorescence microscopy. But there's a fancy gallium arsenide phosphide detector that came out maybe I'd say 5 to 8 years ago, and it's more sensitive in the fluorescence range around green, yellow, and orange, but it's more fragile. And because I work with Hamamatsu with Blake Photonics, I know that there's another model that's coming because we have access to the prototypes. So they have a new one that's more sensitive, less fragile. So it will at some point take over. Unfortunately, it's 10 times more expensive. But the point is that we pick PMTs based on the sensitivity of the photocathode. And then we provide, to get this acceleration, we need to provide a high voltage, like thousands of volts. Well, thousands, hundreds, okay? So a long time ago, they were very difficult to work with because you had to have your high voltage source with you in the lab. When I was doing my PhD, we had, you know, batteries for 1,000 volts in our lab, and then we would just connect everything. But these days, it's fairly easy to get, it's called a voltage ladder that will switch. It will switch a low voltage signal into a high voltage signal, and it's now more convenient. That's all I can say, really. And I'll show you. Well, actually, I'll just go very quickly. But you can now. This is what the tube looks like. But you connect them. 90% of the market for photomultiplier tubes is Hamamatsu. There's actually just one other company that makes PMT, just one that I know, and they're called photoelectron tubes. That's it. So Hamamatsu is very much the standard. So this is, over the years, they made these, they're called sockets. So you take, this is the PMT, and you connect it into this socket. And the socket will take care of all the high voltage components for you. And even you can have an amplifier inside. So they're now simpler to use. And because they're simpler, they're okay to use. And so the high voltage component was a problem some time ago, but that's only because I'm old that I'm talking about it. Okay. And yeah, okay. So I said everything I had to say. And the gain is very high. It can be on the order of 1 million. And it's true that I need to add one more aspect. With all PMTs, you can adjust the gain. You can adjust the voltage on these diodes, dinodes here, and here. So typically, you have a knob, and you'll adjust the voltage. So you could have, say, let's say 1,000 volts between the last one and the first one, or you could have 500 volts, or et cetera, et cetera. So you can adjust that. So on a microscope, on a Zeiss microscope or a Olympus microscope, this in the software, this is the tube gain, okay? And by changing the gain or the voltage, usually in most software, it's just going to be 0 to 100%, and you'll adjust that. And 100% is going to be 1,000 volts, and anything in between is going to be a smaller voltage. So when you do that, you change the gain. And one thing that I really want you to appreciate, especially biologists, Valérie, Vincent, and Julien, but also physicists, there is an optimal voltage for a PMT. So I've been in the lab several times with students, because let's say a project is not working well. So sometimes I get involved because I like the lab, and people will say, yeah, it's not working. My system photo bleaches very quickly, et cetera, et cetera. And sometimes people will have a high laser power and a low voltage on the detector. But that's very wrong. You don't want to have a lot of power and reduce the sensitivity of your detector, because then you're shining a lot of light on your fluorophores. You're creating radicals, you're photo bleaching your fluorophore, and you have your detector that is supposed to be super sensitive, but you're using it with much less sensitivity. So that's no good. You really want to have the voltage on the PMT as high as is acceptable and a low laser power. And because you understand that, let's say 100% laser power with 10% detectivity, or 100% detectivity with 10% laser power, that will give you the same signal in your images, but one of them is shining 10 times more light onto your molecules. So I see that it's actually an extremely common error. People, because it's so much simpler. There's a knob for the PMT that is very easy. It's very often I blame actually the microscope companies, because the adjustment of the gain of the PMT is very easy and it's very convenient. It's always there, and the laser is usually controlled elsewhere in the software. So because the microscope companies don't make the software, so they don't make the lasers. So the laser power is elsewhere, and people will just adjust the detectors because that's what they know and that's where they are. But really, you should have usually 80 to 90% of the maximum voltage is optimal. It's a rule of thumb here, because if you have too high a voltage, you'll start getting noise, because electrons will start being emitted randomly and will be amplified. So 100% is rarely optimal, but it's usually very close to 100%. And then you keep the laser power lower. Okay, so that was my little moment. Yes. So the gain is important, and you want to use it with as much gain as possible, really. Okay. As I said, the sensitivity of these PMTs depends on the material. Yeah, okay. Here it's written. Yeah, you see my screen. Okay, here it's written. It's written in code names, but you have the names of the photocathodes, or the numbers R955, R928. And others R3896, et cetera, et cetera. So the photocathode material will give you the sensitivity, and this is a very typical PMT, and you'll see that they tend to cut off at around 900, or actually the real number is 880 nanometers. Okay, so above 880 nanometers, you're screwed. You can't use a PMT. Which is not entirely true. There's one PMT that works all the way to 1200 nanometer, 1300 nanometers, and it's worth $100,000. But I have known someone who bought that just for a specific project, and it worked. But the point is that remember that it's approximately 880 is a good number. And if you were to do you'll see that they will say, if you look at the specifications for a PMT, it's going to be discussed in terms of radiant sensitivity of the cathode. So you see that they will talk in terms of cathode sensitivity. They say for 1 watt, you will get 0.5 amps at, here you see milliamps per watt, but typically the number it's fairly typical to have 0.1 to 0.5 amps per watt. So that's the photocathode. And then after that, you have the gain. So the initial sensitivity is on the cathode, and then you amplify that that signal with the diodes. Okay. Yeah, and they look like this. So this is really, this is the R3896. I have tons of those in my lab, and these are called the sockets. So the tube is, there are various forms. They can look like this. They can look like this here. But the point is that you use the right tube with the right socket, and then you're all set. Okay, and I just wanted to say, yeah, one final thing. Sometimes it will happen in your microscope that you may have, you may turn on the lights. If you turn on the lights, you can imagine that a PMT being sensitive to photons, if you turn on the lights while it's on, then you'll have tons of current. If it can see photons and all of a sudden you're sending sunlight, that's tons of light. So it's tons of current in the diodes, and it doesn't like that. And there's a trick, actually. You'll see that because sometimes it will break the PMTs. That happens. Or it will make them very noisy. Okay, and the best way to check is that you take another tube that you haven't touched, and you measure the signal in the dark, and you'll see that in the dark, one of them will be very noisy, the other one will not be noisy. So the noisy one, we say, was blinded because it got too much light. So one way to sometimes repair them is to put them in a black box and turn them on in the dark for a day or two, and I don't know what it does except that it sometimes fixes them. But if you bust a PMT, that's one thing you can do. Well, not bust, but if you blind a PMT, that's something you can do to try to fix it. Okay. Yeah.
Question. If you use that trick, what kind of voltage should you apply on the PMT while you put it in the dark?
80 to 90%, close to maximum.
Okay, some operation voltage.
Yeah, exactly. Yeah.
Okay.
And yeah, and it has to be in the dark. It's very important. Yeah, pure, pristine dark. Okay. So now, oh yeah, and yeah, the way that they're connected, the way they are connected, they create a current again. So we need to use what's called a transimpedance amplifier again, so that we change this current into a voltage. So that's why most of the time we take diodes like this, sockets that already have the amplifier. In my lab, we always buy them with the transimpedance amplifier included in the socket. All right, tons of details. There's one tiny thing that I want to discuss. It's photon counting versus analog detection. What do we mean? What do we mean? If you look at the screen of a PMT, the screen of a PMT, that's what I just said is so stupid. If you look at the screen of an oscilloscope that is connected to a PMT, there we go, you'll have a voltage that goes up and down in spikes. And typically the time here is hundreds of nanoseconds. So when you have a photon that hits the PMT, you'll see ping, a peak, and then a decay. So every time it goes bing, 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 you know it's a photon, except when the signal is a little bit lower. Let's say you can have a thermal electron that is emitted from one of the diodes for thermal reasons. And if it's emitted from, let's say, the center diode, then it's not going to be amplified as much. So then you'll have, I'm sorry, a lower signal. So when you look at your analog signal, you have large peaks that are most likely photons, and you have lower peaks, let's say very low peaks that are just noise, and you have in between where you're not sure exactly what this is. It could be a photon, it could be something else. Because the gain is random in the diode, so you don't know exactly what gain. When I say we get a gain of 1 million, it's a gain of an average gain of 1 million. Sometimes you get 1 million, sometimes you get 1,000,000 and 100,000, sometimes you get 900,000. So the gain, I'm sorry, is not always the same because it's a random process. So if you are measuring the voltage, that means sometimes you'll measure, say, 1 volt for a photon. Sometimes you'll measure 1.2 volts. Sometimes you'll measure less. So you should wonder. That means that every time that I detect a photon by measuring the voltage, I don't always get the same value, yet I know it's 1 photon. So if you just digitize the voltages, you will get what's called analog noise because you don't get a peak that is always the same value for each photon. So you could say, wait a minute. What I'll do is every time that it goes above a certain value, I'll say, okay, it's a photon. So you will count 1. And if it's below a certain threshold, you'll count 0. So now at the end of the day, here, you would have a certain voltage, another voltage, another voltage. So you'll have 3 values that are different for 3 photons. But if instead you use a threshold and you say, if it's above a certain value, I'll count this as a photon, then you'll have 1, 2, 3. And there's no noise. If counting 1, 2, 3, it's not 3.1. If you count, you count. So it's 1, 2, 3. So counting photons will reduce the noise that you get from analog measurements of the voltages. Okay. And now you may be wondering, why is it that we don't always count photons in microscopes? Most microscopes do not count photons. They actually measure the voltages, and that means that there's a little bit of a noise associated with, or variability associated with the voltages. The reason why it's done like this is that I'm somewhat showing it here, but do you see that if, let's say, if I have 2 photons that are coming real close to each other, and you use a threshold, then if you have 2 photons at the same time, you'll still count that as 1 photon, because let's say if I draw this here, if you have 1 photon, or if you have another one that comes right after like this, the signal is going to be higher, but if you use a threshold, you'll still say 1. So the photon counting mode works when you have a small number of photons. When you don't have a lot of photons and they don't overlap, then that's good, because you're saying, oh, as long as it's above a certain value, that's 1, 2, 3, 4. But then if you start getting tons at the same time, then you will count 1 even if you had 2 at the same time. So this photon counting mode only works for very low photon fluxes or very low powers. And it's not clear that in commercial systems, it's not clear that the user would know when to switch from a low photon count to a high photon count, so analog values to digital values, so photon counting to analog measurements. So it's a bit rare, okay? It's a bit rare. There are some microscopes that do it, but it's not easy to manage with the user. All right. Okay, so photon counting for super low photon fluxes, photon counting is by far the best. So Shadi, in spectroscopy, we do use photon counting, and it does make a huge difference because we don't have tons of photons. So yeah, so that's what I wanted to say. In very low photon counts, photon counting is really the best strategy. Okay, so yeah, and then whoops. Okay, then the CCD, the CCD, the infamous camera. It's actually fairly simple to understand a CCD. All the other detectors that I described before are all called point detectors because they detect there's one area, the light creates electrons in that area, and we measure a current. But the CCD really, or the charge couple device, is really several photodiodes put together in some sort of an array. So each little pixel is essentially a photodiode. It's a photodiode that is connected into a bucket. So you have the photodiode, and I told you that you can connect, usually you put a voltage and you connect it a certain way. Well, the way this is done is that it creates, when the electrons are created, they're put into a bucket, a capacitor, and then the capacitor will accumulate all the charges, and then you can measure the voltage, or you measure the number of charges by measuring the voltage inside this capacitor, and that will give you the number of charges, so the amount of light. So it's really one photon will hit the detector, will create an electron, will create an electron that will go into a bucket and will accumulate. So the CCD will accumulate the electrons, and after a certain time, you will say, all right, we're done here. Let's just read how many electrons I have in each pixel. And the way the CCD does it is, and it is important because it's different from the CMOS. The CCD will then take each line in the camera and kind of transfer them into what's called the shift register. And then there's a master let's call that the master reader. With the master reader here will measure in each bucket how many charges there are, and we'll do each of them. It's one master doing the reading for everyone. Okay, so the CCDs tend to be sensitive but a tiny bit slow. Okay, or limited in speed. We'll just say limited in speed a little bit, because you need to take one line, and then next line, and then next line, and it takes time to read all the lines. Okay, because you read each pixel one after the other. Okay. Yeah, okay. This is not important, and this is old. Okay, the one thing that can be done is there's so for each photon you only get one electron, but again, you know that we know that one electron will be hard to measure. So if we can get more electrons per photon, we know we're going to be happier. Okay, so in the process, in the shift register, there's something that can be done where as you transfer, you amplify the number of electrons in each bucket by just going very brusquely or abruptly, by switching so hard that if you have one electron, you'll create 50 electrons as you shuffle them to the detector. So that's called an electron multiplying CCD. This is very common. Okay, photometrics has, and they're called EM CCDs. I think it's photometrics has a lot of EM CCDs, and I think the patent for the EM CCD is reaching an end. So I think they're going to be more widely used. Well, they are widely used, but I think the chip here is the EM chip is only by one supplier. I'm not entirely sure. I'll need to double check that, but it was the case some time ago. But the point, so what do we have here? We have a CCD, but it looks like each pixel is somewhat like an avalanche photodiode. So the EM, the standard CCD is good and sensitive. The EM CCD is more sensitive because it amplifies the signal. So it's going to be 50 to 100 times more sensitive than a regular camera. The problem is that it can be fragile. And in microscopy, this hasn't been, it's the benefits of EMCCDs is not in the situations that we use the most in fluorescence. So they work, they work, but they're more common in other areas like astronomy, because we have the CMOS cameras, and I noticed that it must be an old version of my slides because I don't have my CMOS slide, but I will describe the CMOS in one sentence. I told you that for the CCD, there's one single master. Where's my master? Where's my master? Yeah, right here. There's a single master. The CMOS has one little reader per bucket, per pixel. So the CMOS is a very different strategy compared to the CCD, because instead of having several photodiodes that you read one after the other, the CMOS has each pixel is a little detector with a little digitizer and a little amplifier. Everyone has their every pixel has their own electronics, and it's made using processes that are similar to computer chips. So they're made, you make everything at once on big wafers, on big, on circuits, on printed circuits. So it's very cheap to make them because you can make thousands at once. The problem, okay, the problem is that each pixel will be slightly different because they all have their own digitizers and their own amplifiers. Then they can all be different. And for our phones, it doesn't matter. We don't care. Who cares if this pixel has a little bit, is a fraction of a percent more sensitive than this other pixel? We don't really care. But in science, we do care. So that's why you can get these cheap cameras. I bought one for an Arduino that cost me $10. It's very cheap. A CMOS camera, and $10 is very expensive for a phone or for a user. For a consumable, but it's still much cheaper than a CCD. And so that's, at some point, companies joined their forces and created the scientific CMOS, where they fixed all the little details for that CMOS had. So all the little flaws, the amplifiers that are not the same, the digitizers that are not the same, the uniformity, blah, 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 blah. So they all work together, and they created this super fancy CMOS called the S-CMOS that is awesome, but unfortunately also much more expensive. So in the end, the reason why I'm discussing it, and I'm very unhappy that I don't have my slide, is that the S-CMOS is the chip that is the most common in fluorescence, because it is essentially as good as a CCD, but it's much faster. You can do 100 frames per second, 1,000 frames per second for very large cameras, because you digitize everything at once. Whereas the CCD, you digitize everything 1 pixel at a time, essentially, or 2 pixels at a time. But the point is, it's not just like the S-CMOS. But unfortunately, or I suspect, although I'm not sure because I'm not an expert in the field, but the S-CMOS is essentially as expensive as a good EM CCD. I think it's much cheaper to make, but they still sell approximately the same price because it's approximately equivalent. It's even better for us in fluorescence microscopy. So really, an S-CMOS camera now is $25,000, even if originally the CMOS technology was supposed to promise very cheap cameras. It didn't materialize because in the end, people wanted so much that I think the prices are, I don't want to say artificially high, but let's say the prices are what people are willing to pay. So the S-CMOS is very expensive, just like an expensive CCD camera. But the Hamamatsu Orca Flash is an S-CMOS camera. It's a very standard camera. We have a few in my lab, but I would say that I would suspect that most S-CMOS cameras today, most cameras in labs, no, many cameras in labs are S-CMOS cameras. Okay. Yeah, this I'm not sure if we have. I love discussing this, but I think it's going to be too complicated for us. What time is it? If I say poisson noise, what do people say? Vincent says, maybe. Julien, Valérie? Yeah, yeah, yeah. You say yes, or you say yes because you know I want to hear yes.
Well, I did hear about it and I did see it in other classes.
Okay. All right. I'll try to be, I will not get in the details, but it is super important because it is how you can plan your experiments properly in the lab. Let's say, if we play heads or tails, pile ou face, heads or tails, we all know, at least intuitively, that if I flip a coin for 1,000 times, we know that on average I'll have half on head and half on tails, right? We all know that. Yet, if we had to bet, would anyone bet, let's say $100, that I'm gonna have, well, let's say I flip 100 times. Okay, 100 is gonna be it's a good number. So if I flip a coin 100 times, no one is gonna bet $100 that I get exactly 50-50. Nobody would do that intuitively. Yet we all know that on average, this will be true. You know that if I flip a coin 100 times and I do that 100 times and I average all of that, I should get approximately 50-50. We know that. So there is, and we know that it gets better as if I flip a coin twice, okay, I'll flip a coin twice, and then I'll flip a coin 10 times and 100 times. If I flip a coin, let's say 1,000,000 times, 1,000,000 times, so we expect approximately 500,000 heads and 500,000 tails. Well, would you accept to bet $100 that I would get between 550,000 and 450,000? See, if I give you a range, you probably start willing to edge your chances and say, at some point, I'll be willing to bet. Okay? So if I say, I'm going to flip a coin 100 times, and I'll give you a range, 50% plus or minus 1, or let's say 50 in each plus or minus 1, or 50 plus or minus 10. Well, plus or minus 10, you're going to start thinking, yeah, that's not bad. But if I say plus or minus 1, you're going to say, yeah, I don't know. I don't like my chances. Okay, now I'm going to tell you something that may surprise you. But in a completely random process like flipping a coin, we actually know the spread of the distribution. So if I were to flip a coin 100 times, let's say I do that, I flip a coin 100 times. Then I flip a coin 100 times. And we keep that as separate experiments. So I have done, each time I flip a coin 100 times, I will get 50%, essentially plus or minus 10%. I actually know that. So 66% of the time, I will get something between 50 plus or minus 10%. Now you're thinking, what kind of black magic trick is this? Okay, there is something, it's the Poisson distribution. But for things that are completely random, okay, and that are, let's call that discrete. So flipping a coin, for flipping a coin, I could say head is 1 and tails is 0, right? I could say 0, 0, 1, 1, 0, 1, 0, 1. So it's a process that's discrete. It's not 0.2, okay? So for something like this, when I count stuff, okay, the error that I have, the uncertainty or the distribution is 1 over the square root of the number of measurements. And to me, this was so magical, and I really did not understand where it came from when I was first told. And the proof is actually not particularly difficult for the mathematically inclined. But what you have to remember, and I'll show you with a graph, okay, is that if we actually know intuitively that result. You know that. You know that the more I flip my coin, the more likely the average is going to be close to 50-50. Not all the time, but you expect it. Okay, you expect that the average will converge. Well, if you look at the average, so what do I have on this graph? I flipped a coin with a small computer program, okay? And I assumed that heads was 1 and tails was 0. And then I took the average, okay? So if I flip a coin once, sometimes I got 1, sometimes I got 0. Then if I flipped a coin twice or 10 times, if I look 10 times, I did it several times. So after at 10 times, okay, so I flipped my coin 10 times. It happened once that I got an average of 0.8. So that means I had 8 tails and 2 heads. And sometimes I got the opposite, et cetera, et cetera. But you can see that they're all spread within a certain range. And that range is getting smaller and smaller and smaller as I do that more and more and more. This curve here is really 1 over the square root of number of times that I did that measurements. And you're thinking, why is he talking about this? Well, when we measure photons, we flip our photon coin. Sometimes there's a photon, and sometimes there's no photon. It's essentially the same as head and tails and flipping a coin, except that let's say you're more likely to have nothing than have a photon. Let's say you have 1 photon per second and you make a measurement every nanosecond. Well, essentially 1 billion times you'll get nothing, and once every now and then you'll get a photon. But the noise on counting the photons will be in 1 over the square root of the number of photons. This is weird. This is weird. You should be a little bit alarmed. At the same time, I'm telling you, this is a highly mathematical and proven phenomenon. Okay, the Poisson distribution has a width that is the square root of the number of events. So for us, what that means, and it is important for Valérie Vincent. Well, actually, it's not important just for Valérie Vincent engineering. It's important for everyone. But if you measure an intensity or a light signal, and you have, let's say, a noise of 10%. So let's say there are tons of examples for this. You have a camera, you have your microscope, and you measure an intensity of, I don't know, a certain value, it doesn't matter, that 250. It doesn't matter what the units are. You measure 250. Right after that, you measure, no, let's say you measure 100. We'll take easy numbers. You measure 100. Then you do it again. You measure 109, and then 92, and then 98, and 105. And you take the measurement several times, and you have a noise of 10%. Well, maybe you are interested in seeing a 1% change in that intensity. Maybe you're measuring a phase difference. Maybe you're measuring a calcium fluorescence difference. Maybe you are interested in seeing something, a small change in that value. And you're going to say, oh, crap, I have 10% noise. There's nothing I can do. Well, that's not true. There are two things you can do. The first thing you can do is you can say, well, I'll just measure for a longer time. For instance, Emil is trying to measure the phase, and he needs the intensity, and he's going to take the difference between two intensities. Well, if 10% is too much noise, well, if 1% was a good noise, well, that means you have to measure 100 times longer. Okay, if you measure 100 times more, you will reduce the noise by 1 over square root of 100. So that's 1 in 10. So if you measure 10 times longer, I'm sorry, 100 times longer, you'll reduce the noise by 10%. To 10%. You'll divide the noise by 10. Okay, so in this case, you would say, aha, because I have time, I'll just measure more photons for a longer time to reduce the noise by a factor of 10. So 100 times longer for 10 times better noise. Let's say Valérie is saying, no. Valérie and Vincent are saying, no, I don't have time. I don't have time. I have no time. No time. I cannot measure for a longer time because my calcium signal is changing. Well, they could say, all right, I'll then pool the value of the fluorescence from several pixels because I know that the calcium signal is really the same in all of my cell. So I'll just add everything together. So let's say if I have 1 pixel that has a noise of 10%, and I have 100 pixels for my cell, if I add all the signals and they're approximately the same, they all have 10% noise. If I add them all up, then the noise is going to go down by a factor of 10, down to 1%. So then all of a sudden, this calcium signal that you were trying to see and that you knew was only a difference of 10%, you say, well, it's a 10% difference, but I have 10% noise. What the hell can I do? Well, if you pull the pixels, all of a sudden your noise goes down to 1%, and then you can see your signal, your calcium signal. So this whole photon noise thing is really a mathematical concept that is, there are two things actually. The first one is the Poisson distribution. The Poisson distribution has an extent that depends on the square root of the number of events. And the Poisson distribution is what we have when things are completely random. And measuring photons, we say it's completely random, okay? And then you talk to theorists, they're going to say, oh, good Lord, how can you say that? You know, it's not, we all know that that's not a Poisson distribution. The thing is, over extended periods of time, things will converge to Poisson distributions. And this is actually mathematically proven, that it's called the central limit theorem, that eventually everything turns into a Gaussian. And a Gaussian is a type of Poisson distribution. Okay, so why did I say all of that? Okay, why did I say all of that? This is the first, and when everyone goes in the lab, at some point they're trying to measure something, and at some point there's noise, and they come back to the group and they say, I don't know what to do. I have 10% noise, and I'm trying to see this small thing that's 1%. What can I do? Well, it always turns into, how can you get more events? Well, maybe the solution is just crank up the bloody laser power. If you have 100 times more power, your problem is solved, as long as your sample is not burned. So maybe you should buy this PMT that's 10 times more sensitive, because you'll have 10 times more signal. So square root of 10, 30% better noise characteristics. And all of that, sometimes, going from an avalanche photodiode that has a gain of 100 to, whoa, all of a sudden a PMT that has 1,000,000. So that's 10 to the 4 of difference. So you're seeing 10 to the 4 more photons. So the possibility is to get noise that's 100 times better. Okay, so all of those things are, I find this understanding of how the noise behaves with your intensity, your detected intensity, is really critical for all of you. I've solved tons of lab problems with students by looking at this and say, well, okay, we can't increase the power because we're gonna kill the mouse. The detector, no, the laser, we don't have a more powerful laser because blah blah blah. No, we can't. No, okay, there you go. This dichroic mirror that we're using has absolutely shitty characteristics at this wavelength. There's another one here that's blah, blah, blah. Or we can take a lens that's twice as big to get 4 times as much light. All of these things at some point can be quantified, and to decide where you're going to put your money. And if you're in no rush, you can always integrate for longer and measure for a longer time. If I'm in no rush, if all I want is to graduate and my signal is too low, I'll just measure for a minute if I have to. At some point you'll just do whatever you have to do to get the right signal. Is it practical? That's another question. But once you have proven, for instance, I'll just take an example with Elahe and Shadi, because I know the spectroscopy project more. But sometimes the question is there a signal in this tissue coming from Raman blah? And as long as we can prove that there is a signal and that we can use it to differentiate, it doesn't matter if it takes an hour to take the data, because then we can say, all right, let's just get a bigger laser, a more sensitive detector. Let's just do and then you can quantify. So this here is really something that removes the guesswork out of your lab work. Okay. All right. So so you can always say, I will get 100 times more blah to reduce my noise by a factor of 10. Just remember that. This is so useful, because people have a tendency to think that if I measure 100 times longer, my noise is going to get better by 100. No, it's the square root of 100. Okay. All right. And my final slide, really. This is my summary slide. Okay, it is a useful slide. So you have all types of detectors that we have discussed: the power meter, the photovoltaic photodiode, the photoconductive photodiode, the avalanche photodiode, the photomultiplier tube, the solid state photomultipliers that are really just avalanche photodiodes but in an array, the CCD, and the electron multiplying CCD. They have a certain speed. Okay, we say speed as in the rate at which you can get your data. So a power meter is slow. An avalanche photodiode is very fast. You have a gain. So the gain is how many electrons are you getting per photon. So this is the thing. This is really the column that's the most important for you, because things will be possible because the signal is high enough, and the high enough will usually be because of the gain. Okay, so the gain is really important, and now you know that sometimes it's sufficient with small photodiodes, but then you can have an avalanche photodiode that's not so difficult to use, or a PMT. A PMT is more sensitive, but the gain is very, 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 very significant. Okay. And then you will notice that I'm using here the response, or the value in volts but this is really a detail. The thing that you tend to you will tend to look at is the sensitivity. Oh no, I meant responsivity. Yeah, I didn't write that table right. When you purchase a diode or a detector, you will see number of volts per watt. So that's going to give you an idea of what type of signal you have, and that's obviously related to the gain and the spectral response of the detector. Okay, so really, I hope I have a few questions, but I'll give them to you as assignment questions. There's a lot. In what I said today, I hope this was considered useful to you guys, but I tried to give you an overview of all the detectors and the tools, or the key parameters to look for when you want to select them, or exactly if you have a certain problem, what you need to do to improve it. So if actually you always want to, it's the price of these detectors is essentially like this. This is cheap, this is not cheap. Okay, so anytime you can use a cheap detector, you should use it if it's sufficient, but then you need to know when you have to go up in price. Okay, let's price performance, essentially the same in our world. So I have questions that I'll give you as assignments, and they will be just about estimating numbers. Okay, it's all about estimating numbers. So so I hope it shouldn't be difficult. It's mostly estimates. So let me know if you have, well, first of all, do you have questions from today? I hope this was useful. I hope this wasn't too boring. And I hope that the biologists got some of the feel for the things to look for and the things you can do in the lab. I hope. If not, you can always ask me questions. I'm here for that. Okay, so if we don't have any other questions, I only got the assignments last night. I was a little bit tired last night. I didn't have time to look at all but I'll give you I have all the solutions for the assignment that I gave you. And if you have questions, then we can discuss that. All right. Okay. So we're Thursday, so I think we'll have the next class. Yeah, Monday is my group meeting. So do I have something Monday afternoon?
Yeah, at 1 p.m.
Yeah, we have something at 1 p.m. So Tuesday morning, how's Tuesday morning? Tuesday morning good?
I can't be there at 9. Can we start at 9:30?
Oh, yeah. No problem. We can all sleep in, including me. I'm getting shifted. I'm shifting towards, getting up later and later and later these days.
I'm having my French class from 8 to 9:30.
Okay. Oh, well, for French, we can do anything for French. Yeah.
Thank you.
All right. Excellent. So, all right. I'll see you soon.
Great, thank you.
Thank you.
Yes.
Bye-bye.
Thank you.
Bye.
Bye.
Bye.